Welcome to Lesson 1, What is Heat? Our lesson objectives: determine the direction of heat flow, identify substances with the highest average kinetic energy, determine if a reaction is endo or exothermic, and use Table I to determine the change in heat of a reaction. Recall we have two types of energy. We have potential energy, which is stored energy, and we have the energy of motion, which is known as kinetic energy. So what is heat? Heat is the movement of energy from one object to another. So it's going to move from the hotter object to the cooler object. As you can see here in the animation, if we apply heat to this one particle here, we see that the heat then is radiating or being transferred out from the hotter object to the cooler objects. And it's going to do so until we reach thermal equilibrium, until everything is the same temperature in a closed system. Here's an example. If the room is 22 degrees Celsius and I place hot chocolate in the room, the hot chocolate is 80 degrees Celsius and the room is 22. So the hot chocolate has more heat energy. The particles are moving faster, has more kinetic energy, and overall the energy is going to then be lost or transferred to the room until the hot chocolate is the same temperature as the room. In this example here, the room is 22 degrees Celsius and the ice cream is -4 degrees Celsius. So the room has more heat energy, and so that heat energy is going to be transferred to the ice cream, warming up the ice cream until the ice cream reaches the same temperature as the room. Here's another example. In terms of heat flow, what happens when an ice pack is placed on your skin? Now, it's often thought that the ice pack is going to transfer cold to your skin, and that's not the case. We're talking about heat, we're talking about energy. So what's happening is that our skin is 37 degrees Celsius and the ice pack is 0 degrees Celsius. And so heat energy is going to be transferred from our skin to the ice pack, in essence warming up the ice pack. As it's doing that, it's drawing heat from the skin on our arm or our hand, and it makes the temperature decrease, and so it feels colder. And it's going to keep doing this until the ice pack reaches thermal equilibrium with our skin. So we defined what heat is. Now, what is temperature? Well, temperature is the measure of the average kinetic energy. Remember, kinetic energy being energy of motion, as we see these particles moving here. So it's a measure of that average kinetic energy of the particles in matter. So if they're moving slowly, a lower average kinetic energy translates to a lower temperature. If they're moving faster, a higher average kinetic energy translates to a higher absolute temperature. As you can see in the animation here, when the particles are moving slowly to when they're moving quickly, we can see that temperature increases. So here's an example. In which sample of water do the molecules have the highest average kinetic energy? So again, kinetic energy being energy of motion. And so if you recall, average kinetic energy is a definition of temperature. So we can replace that with the word temperature. And now the question is much easier. In which sample of water do the molecules have the highest temperature? Well, in that case, it's going to be the first one, which is 100 degrees Celsius. So the question is basically asking, which sample of water are the molecules moving the most? Well, they're moving the most when they have the highest temperature, the highest average kinetic energy, energy of motion. So let's check your understanding. Can you determine the direction of heat flow, and can you identify substances with the highest average kinetic energy? Now let's focus on energy changes during our reactions. We have exothermic reactions, exo like exit and therm meaning heat. So the heat energy or energy is being released from the reaction or produced. So reactions release energy or heat. Energy is located on the right-hand side of the equation, indicating that it's produced. It's a product, so it's being given off or released. And exothermic reactions are more stable due to that release of energy. If we are getting rid of energy, our stability increases. And these reactions will happen more often in nature because they require less energy to get them going. So a good example of an exothermic reaction would be a hand warmer. Endothermic reactions, endo like taking in, therm in heat, reactions are absorbing energy or heat. And so we show that in our equation by putting the energy on the left-hand side of the arrow. It's taking in as a reactant. And so a good example of that would be a cold pack. A cold pack is taking in heat energy from the surrounding environment, around the bag, and that's why it feels much cooler. In our reference table, we have table I, which shows some energy changes. And so the symbol here, delta H, delta means change in, so it's the change in energy of a reaction, and it's located on the right-hand side of table I in kilojoules per mole. On the bottom, it tells you a minus sign indicates an exothermic reaction. And so exo meaning heat is being produced or lost. And so a negative delta H indicates that more energy is being released than is being absorbed. So then a positive delta H, an endothermic reaction, more energy than overall is going to be absorbed. So let's see an example. When C2H4 is formed or produced, is heat released or absorbed? Well, I first find the formation of C2H4, which I have here cut out of table I. So we're making C2H4. I look at the delta H value and it's positive. And we know if we go back here, on the bottom it says a minus sign indicates exothermic reactions. So that this positive sign must be endothermic reaction, meaning it's absorbing that 52.4 kilojoules of heat. So where would the heat go? It would go on the left-hand side of the reaction. It's a reactant. We're adding heat to get this reaction to go. What happens if it's reverse? So if they ask you, when C2H4 is broken down or decomposed, is heat released or absorbed? Well, here, as we saw in the previous example, we were forming C2H4. So reverse reaction, if we're going to break it down, we're going to reverse the reaction and go back to the left. So I'm actually just going to rewrite that as we see here. So C2H4 produces 2C, 2H2, and 52.4 kilojoules of heat. And so what did we do here? Well, now we have energy on the right-hand side. So here, energy was on the left. We were absorbing. So now it's on the right. We are producing or releasing, which makes it exothermic. So in essence, when we reverse the reaction, the number stays the same. We just reverse the sign. We just switch the sign. So it's a negative 52.4 kilojoules of heat energy is released in the breaking down of C2H4. Let's check your understanding. Can you determine if a reaction is endo or exothermic? And can you use table I to determine the change in heat of a reaction? At this point, you should be able to determine the direction of heat flow, identify substances with the highest average kinetic energy, determine if a reaction is endo or exothermic, and use table I to determine the change in heat of a reaction.